Welcome back to the next tutorial in electrical machines. We will discuss few problems on single-phase induction motor. This is the first part of single-phase induction motor. Another two parts are also there. So let us see some problems in this part. Problem number 1, where there is a single-phase induction motor which is of 6-pole 50 Hz rating. The machine is running at a speed of 900 RPM. We have to determine the frequency of the current in the cage rotor. So the construction of the rotor is basically the squirrel cage induction motor, and this is single phase. 3-phase we have already covered. So let us see how to solve the single phase induction motor problem for here where the speed is 900 RPM. What is the frequency of the current? If you remember, in the 3-phase induction motor we have discussed that the frequency of the rotor current is basically slip time the supply frequency. However, this is different in single phase induction motor case because you have the concept of double revolving field theory which we have discussed in the lecture. So let us see the solution. First we have to obtain the synchronous speed at which the magnetic field is rotating, given the formula 120 F by P. Here F is basically the frequency which is 150 Hz and the number of poles of the machine is 6. Hence we get 1000 RPM, the speed at which the magnetic field is rotating. The slip of the rotor at which the rotor is rotating can be obtained using the formula as the difference of the speed between the stator magnetic field and the actual speed at which the rotor is rotating. The reference we take as the synchronous speed and then it is multiplied with 100. The synchronous speed we have calculated as 1000 RPM. The rotor actually it is rotating at 900 RPM. So the slip comes to be 0.1, which is equivalent to 10%. The frequency of the two rotor current, because it is a double revolving field, will be obtained using the formula S into F. This is similar to the 3-phase induction motor. However, there is the concept of forward field and the backward field. The backward field will have the frequency 2 minus S multiplied with the supply frequency. Supply frequency is 50 Hz and the slip is 0.1. So we get 2 rotor current frequency as slip time the supply frequency and 2 minus slip, which gives to be 5 Hz and 95 Hz. So these are the frequency of the rotor current due to the forward field and the backward field. Problem number 2. Again, we have a single phase motor. The rating on the motor is given as 2 horsepower and it is supplying a voltage 240 volt AC. So this is the input to the motor and the efficiency of the motor is given to be 70%, where the power factor of the supply is 0.8. Find the input current. Let us see the solution. It is to be remembered that 1 horsepower is equivalent to 746 watt. So the total output power of the induction motor is 2 horsepower. It means it is equivalent to 2 multiplied with 746, which gives to 1492 watt. The efficiency, which is ratio of the output by input power, can be used to determine the input power as output power by efficiency. Efficiency is 70%, so we can take 0.7 and the output power we have calculated as 1492 watt. So that gives the input power to 2131.43 watt. We have to determine the input current. So we can use the formula of single phase power, which is VI cos phi. So the power which we have calculated as 2131.43, this is the single phase power. The voltage is given 240 volt. The current is the one which we have to estimate and the power factor is 0.8. If we solve this equation, we get the current to be 11.1 ampere. So that is the solution for this problem. The next problem, problem number 3, where you have a 4-pole single phase induction motor. It is rotating in the clockwise direction at a speed of 1000 RPM, having a voltage of 100 volt with a frequency 50 Hz. At a standstill condition, if the rotor resistance is 1.7 ohms, then in the backward branch, what will be the effective resistance? So it is rotating in the clockwise and we have double revolving field concept where forward field and backward field will be there. So we have to calculate for the backward field what is the effective resistance of the motor. Let us see the solution. The effective rotor resistance in the backward branch will be equal to the rotor resistance at the standstill condition, which is R2 dash, divided by twice the slip value. So this is for the forward branch. Now for the backward branch, if we have to calculate, then the denominator instead of 2s will become 2 times 2 minus s, because the two slip that we have is basically s and 2 minus s. So the backward branch will have this formula and the forward branch will have this formula. This rotor resistance R2 dash is basically the standstill rotor resistance, which is referred to the main stator winding. So we are using one dash of the prime to refer that it is in the main winding. It is referred to the stator side. First, we need to calculate the synchronous speed, again with the formula 120 F by P. The frequency given to be 50 Hz and the number of poles is 4. So we get 1500 RPM at the synchronous speed. The shape we can calculate from the synchronous speed, which is 1500 RPM, and the actual speed of the rotor is 1000 RPM divided by the synchronous speed. That gives to be 0.33. Now we can use the formula of the backward branch, the resistance, effective resistance. It is what the question is asking. If the question is asking us the forward branch, then we could have taken the other formula. So this is what we have to take. So here you have the rotor resistance at the standstill condition, and this is the slip value. So we have 2 minus s multiplied with 2. That gives to be 0.5 ohms as the rotor resistance under backward field condition. Problem number 4, we have a 6-pole 50 Hz induction motor. Its equivalent rotor resistance is 0.01 ohm per phase. If its stalling speed is 900 RPM, determine the resistance that must be inserted in the rotor winding per phase to obtain the maximum torque at starting. Now, if we read this question carefully, nowhere it is mentioned that whether it is single-phase induction motor or whether it is 3-phase induction motor. But since the resistance is given per phase, so this is an indication that this question belongs to the category of 3-phase. This question is knowingly added here to make a difference that the problem may be in the category of induction motor, but we have to decide whether it is single phase or 3-phase. If it is not given 3-phase or single phase in the problem, we have to determine it from the other concept, because here it is given that the rotor resistance is per phase, and again we have to determine what resistance you need to insert in the rotor winding per phase. So obviously it is a 3-phase problem. Let's see the solution. Although we have described the 3-phase in another lecture series and we have discussed many problems on 3-phase induction motor. Here the synchronous speed, again we have to first calculate whatever the problem we have for in the induction motor. Each and every time we have to first calculate the synchronous speed. So here the synchronous speed is 120 F by P. The frequency is 50 Hz and the poles is 6. So obviously it is 1000 RPM. And the stalling speed is 900 RPM, that is standstill speed. And the speed or the slip and the stalling condition we can obtain as 0.1. So the difference between the synchronous speed and the rotor speed, rotor actually is rotating at 900 RPM. So you will be getting at 0.1 as the slip condition. Now we have to deal with the maximum torque condition, and we know that the slip is given by R2 by X2. This is the condition for maximum slip. So resistance is not given, and the resistance what is given and the reactance is not given. So resistance is 0.01 and the reactance we have to calculate. So if we put it in the formula where the slip is already known 0.1 and the resistance is given 0.01, so we can calculate the reactance as 0.1 ohm. Now we have to obtain the maximum torque at that condition where the rotor resistance and the starting the slip value is 1. So what is the torque at the starting condition? Starting condition the slip is 1. So we can use again that Sm is the ratio of rotor resistance by rotor reactance. Here the slip value is 1 and the rotor resistance we have to calculate, and the maximum condition we are getting at the very beginning, that is at the starting condition. So the rotor resistance now we get 0.1 ohm per phase, but it is asked what is the extra amount of the resistance that we need to add in the rotor circuit. So already we were having a 0.01 which we have to subtract from 0.1 ohm. So we get the external resistance is 0.09 ohm per phase. Remember, this resistance we can add only in slip ring induction motor, and it is not possible to add any external resistance in a squirrel cage induction motor. So this problem lies for the 3-phase induction motor case. Problem number 5, again we discuss for single phase. So single phase ratings given 230 volt, 50 hertz and 4 pole. This is started by the capacitor start motor. We have discussed many categories of the induction motor starting. 3-phase induction motors are self-starting, and the single-phase induction motor do not start its own. You require some different techniques of starting, usually using a capacitor. So the main winding and the auxiliary winding impedance value are given to us. We have to determine the value of the starting capacitor, which is required to produce 90-degree phase difference between the current in the main and the auxiliary winding. So what is the current which is flowing in the main winding? What is the current which is flowing in the auxiliary winding? And then what is the phase difference of these two current has to maintain at 90 degree. So we need to determine the value of that capacitor that need to be included in the circuit. Let us see the solution. So the given condition we have for the main winding and the auxiliary winding, the impedance value in rectangular complex values, we have to convert that in polar form. So we have the magnitude and the phase. This gives the information of the impedances in magnitude and phase. Now this is the circuit of capacitor start single phase induction motor. Here we have the rotor and the supply which is given as single phase. The two winding, we have the main winding and the auxiliary winding. So this is what we have, the main winding, and here you have the auxiliary winding. Auxiliary winding is used only during the starting of the induction motor. So you have a capacitor which is connected in series with the auxiliary winding. This capacitor is required for the starting of the induction motor. The current which is coming from the supply is distributed in the main winding and the auxiliary winding. So same current is flowing between the capacitor and the auxiliary winding. The difference of these two currents would be 90 degree. That is what given in the condition in the problem. So now it is given that the current IM, that is the current in the main winding, which is lagging the supply voltage by an angle of 32 degree. So we can say that the voltage which is as the reference, and you have the two current, one is auxiliary current and another is the main current. So the main current is lagging the voltage V by an angle of 32 degree. So we can use the concept of the total impedance of the auxiliary winding, because the capacitor whose reactance or the impedance we can say XC 1 by j omega C is added to the auxiliary winding, because both are in series. So that will give the total impedance of the auxiliary winding. We have to put the values of this ZA and 1 by j omega C. Omega frequency we have been given, but the capacitor value is not given. So we can frame one equation in the rectangular system of complex number having the magnitude and the phase. We are interested in the phase value because we have to say that the current angle difference is 90 degree. So this is what you have, the phase difference in the auxiliary winding, which is tan inverse of the imaginary part by the real part. This is from the complex number concept. Now the sum of the angle of the auxiliary winding and the main winding, which comes to be 90 degree. This is what the information is given. We have already seen the 32 degree we have for the main winding, and the auxiliary winding, which is summation of the capacitor and the auxiliary winding. Its phase difference is tan inverse of the quantity given in the bracket. We have to add it. The unknown quantity is basically the omega C. So if we solve this equation, we get 1 by omega C is equal to 20.4. So we have to obtain the capacitor value. We know the formula that omega is 2 pi f. So we can substitute this omega as 2 pi f, where the frequency is already given to be 50 Hz, then we can obtain the capacitor value by solving this equation, which gives 156.03 microfarad. So this is the capacitor which need to be included in the auxiliary winding so that the current difference becomes 90 degree between the main winding and the auxiliary winding. Next problem, where you have 120 volt 60 Hz single phase induction motor, which is again the capacitor start type. The main winding has 180 effective turns and the auxiliary winding has 250 effective turns. These are the number of turns on the winding in the main and the auxiliary. With the rotor stationary, rotor is still at the stationary condition, the input impedance which is given for the main winding and the auxiliary winding, and what we have to determine at the standstill condition is the magnitude of the forward and the backward rotating field, the size of the starting capacitor necessary to yield a single rotating magnetic field at the starting. So these two itemize the list we have to calculate. So let us see the solution. Again, this is single phase induction motor where you have the main winding and the auxiliary winding. A capacitor is connected in the circuit of the auxiliary winding. So the positive and the negative component of the MMF of the single phase induction motor is given by the formula, where M1 represent the positive component and the M2 represent the negative component, is given by, we know that the MMF formula is equal to product of N into I, where N is the number of turns and I is the current. So here you have the main winding number of turns and the current IM in the main winding, auxiliary winding number of turns and the current in the auxiliary winding. And this is a constant which we need to multiply with the vector so that we get the positive and the negative MMF, where J is nothing but the iota term, which is square root of -1. So if we use that equation and split up into two formulas of F, M1 and M2, this is the positive component and this is the negative component, we have half of Nm Im minus J times NaIa. This is the formula for positive component, and the negative component we have where this negative sign is converted to positive, and we can substitute all the data which are provided in the problem, where the number of turns in the main winding is given to be 120. The current we can obtain as the ratio of voltage by impedance. So voltage is given to be 180 and the impedance of the main winding is given to be 5 plus J10. Again, here the auxiliary current what we can obtain is basically V by Z. For the auxiliary, the impedance is already given. So the data that is given in the problem, we can substitute here and we can find what is the MMF of the main winding and the MMF of the auxiliary winding, positive and negative cases. The positive sequence component of these auxiliary winding MMF, FA1, now we can obtain as J times FM1. So this is the positive component of the MMF and this is for the auxiliary winding. So this is what we get for the auxiliary winding positive component. The negative component we have where we put a negative sign and we put the negative MMF that we have got it, that is for the auxiliary winding, we will get the values. Now these two will be added is in a complex number where you have the positive sequence component and the negative sequence component. Negative sequence component is imaginary and the positive sequence component is the real value, but it is complex together. So we get the net forward rotating field which is given in this form. On the other hand, if we want to compute the net backward rotating field, this is for forward where you have FA1 plus J times FM1, where you have the negative, we have FA2. So what we have calculated on the negative sequence component, we can substitute this value of FA2, FM2 also we have calculated, that we put it, we get the net backward rotating field and the net forward rotating field. But the condition is that to have a single rotating field, the backward rotating MMF must be 0, because unless and until you're rotating in the backward direction is 0, the machine will not start. So only the forward rotating field has to be more than the backward rotating field, and you need only one single rotating field. So backward rotating field you equate with 0, and we put it in this equation where the ZA value is unknown to us. On the other hand, we can also say that the impedance of the auxiliary winding is already given ZA value, where the capacitor which is connected is not given to us. So the capacitor, we can put it in the numeric symbolic form as the reactance of the capacitor as Xc. Now we have this equation 1 and the equation 2. These two equations we can equate it and form one third equation. Now here the unknown variable that we have is basically the Xc, because we need to determine what is the capacitor that we need to include in the auxiliary winding. So if we equate the LHS equal to RHS and solve it, we get the value of Xc as 22.44 ohms. Now this is the reactance. Actually we need to obtain the capacitance. So capacitance is nothing but 1 by omega c, where omega is 2 pi f, frequency is given to be 60 hertz, and Xc value is given to be 22.44, which we have calculated. If we solve this equation, we get 118.2 microfarad as the capacitor that need to be included in the auxiliary winding. So this is the first part of single-phase induction motor, where we have discussed few fundamental problems related to double revolving field theory, including the main winding and the auxiliary winding. We had two more parts. The second part we will discuss on the equivalent circuit, and the third part we will discuss on the testing, whether it is a no-load test or the block rotor test of single-phase induction motor, computing its parameter. Thank you for now. See you in the next lecture.